Hello and welcome to week 6. It's getting close to the end of February. Actually, let's go over the syllabus just to check in. Okay, so this is about where we're at. We're heading up on week 6. So we're at chapter 3, the LLMs. This week we're going to be doing text classification. And next week we're going to kind of cover a little bit of BERT and things like that. We do both lectures tonight if I can. Remember, your research project's due on the 28th. So today is Sunday the 23rd, so middle of the week sometime. Uh, Friday night. So, don't forget research project due on Friday night. Okay. So let's take another look. So I've had a couple people ask me about the midterms. I don't even know where it is on this. A lot of times I know people throw it at spring break. Do I even have a midterm listed? If I have a midterm listed on here, do I? Yeah, look at that. There's not even a midterm. So why are people emailing me about midterm? So, generally speaking, if I do give a midterm, basically what happens is you can take it as many times as you want. Uh, it's open book, open note, open chat GPT, open Google. They're not super hard. I'm not a big believer in midterms because in the real world, in the business world, in the production world, it's about results, not about, hey, do you know this? Do you know that? So I'm not a real heavy midterm tester in terms of creating them. I think last year for this class, I made like a 2-hour lecture. Well, I know it's horribly long. It was more work for me. But I made like a 2-hour lecture for midterm and made y'all watch it. And then as long as you said, hey, I watched the midterm videos, it was on ethics. Because I really think that's one of the big things that a lot of engineering, MBA, non-medical science people are missing is ethics. And it's not necessarily the ethics of, hey, what's right and wrong, but what, you know, what's possible, what's not possible, what's happening in the world today, things like that. I told some of you, I made an announcement that I gave a speaking event last Thursday, 3 days ago, 4 days ago. And that was one of probably the more common questions related to ethics. What type of safeguards are on chat GPTs? What type, how can I protect my information? Are they tracking me with my phone? Things like this. So I might do that from the midterm, but like I said, guys, the midterm is going to be easy if I give anything. Last year was just like 2 1-hour videos on basically ethics and data ethics and basically just stuff like that. If I give you any type of written test or multiple choice, I'll open up for at least 1 week, probably 2 weeks. You can take it multiple times. You can use notes, use anything you need to pass it. I really don't care. You just can't work with somebody else. So far this class is going good. I think the average is phenomenally high in this class. Like 119 because everyone's doing the extra credit. Don't worry, the extra credit does get a little steeper, it gets a little harder. You have to eventually highlight things, but for now, it's good that people are bulking up on that. The research knocks maybe, like I said, 5 or 10 points off, but still, everyone's doing really, really well. So let's dive in. So this is chapter 3 of the, I don't know, where's that, the Rue book. And a little bit of the old NLP. I'm gonna leave the old lecture up if you guys really want to watch it. It's not bad. Um, with the old book, I just had to put a lot more chapters into one section. It was a little harder to teach. That's really the only difference. This one has a little bit nicer visuals, and it's just organized a little bit more discreetly and a little cleaner. However, I don't know if it's this week or next week, we talk about model selection for like LLMs, and it's a weird place to put it, So this book still has real kind of weird anomalies. Okay, machine intelligence is the last invention that humanity will ever need to make. So Sam Altman, the CEO of ChatGPT, he had a baby, baby boy, baby girl, born a little premature, but I think it was yesterday, or the day before. And I don't remember the exact quote, but he's like, it is weird having a kid when I know that there's LLMs, that there are products out there that will be considerably more intelligent than my kid. And it's true. We're living in a time where knowledge creates knowledge. And that creates a lot of issues. I have, I think, 10 papers that I've had a machine go out, create, run the experiment, test the experiment, kind of do like a little peer review, and then write the actual paper. I mean, full papers, full academic papers that I haven't published. I don't know if I even can publish, but they're 100% just machine created. The experiments were done by machines. The idea was done by machine. Everything was done by a machine. We have machines creating knowledge. And so that's kind of where this quote goes to. So let's see what we have. So again, kind of inside large language models. Maybe next week we'll do BERT, maybe what it is. Talk about the transformer model, and this is where it gets hard. Because how deep do you want to dive? You need to understand the basics, but you don't need to understand the math. You know, if you're going into academia, you're going to go into CS. This transformer model is super important. Attention is all you need. It is the name of the paper, and it changed. It took a year or so, but it changed the way that NLP was really processed, run, understand, and more so not only just NLP but other areas of research. So it really depends on your focus. You're going to go to business and you're going to use ChatGPT. Boom. This class is, I like to think, in depth as much as you need for transformers. You're going to academia, you're going to do research papers on it, you're going to spend a lot more time on this. Just as, you know, I drive my truck back and forth to UNLV. I can't tell you how all 500 some sensors in the truck work. I'm not a mechanic, but I can get back and forth every day to UNLV without a problem. It's how deep of knowledge you need. I cover a few other, you know, zero-shot encoding, Flash, and a few other terms that, you know, they're just updates to the transformer model, like long form, just to kind of like teach you, hey, here's a general idea. So let's quit talking, let's start learning. So now, why transformer models? This was a slide from my last class, but basically, we did a lot of token homework. And a token is basically you just break up a sentence or a paragraph into words or something. Maybe not even words, you know, because you saw sometimes when you lemonize and stem things, you get rid of the ing and you go to the root word. So a token is just the smallest unit of meaning. Okay? We have kind of an autoencoder and autoregressive. Now, or a combination of two. We'll talk a lot about BERT next week. BERT is a bidirectional. It looks at the word kind of before and after, and one of the things it does is mask the input. The quick brown blank jumped over the lazy dog. We all can figure out what that is, okay? Because we understand as humans the masking of it. Autoregressive kind of predicts the next words. I think today is going to be an ice, then day. So, and I have a demo. I wrote a demo just for this class. Just kind of show autoregressive. Autoregressive is really nice, but it also has some problems. Once you put that token in it, there's no going back. So again, high level view. This is more from the book. That last slide was, like I said, from last year. But you know, tokenizer is basically an inputting process. When we tokenize, we have to take words on paper and somehow convert them to a system that the computer can understand. And if I take the word "the" that maybe appears 10 times on that paper and I give it a random number each time, well, it loses context. So we have to, you know, create kind of a dictionary, or we have to have a standard method of doing that. If I change the word running to ran half the time, then the machine, it just doesn't work. I mean, we have to have consistency. That's why that tokenizing homework that we did last week, it was kind of weird. I know in terms of like, hey, why am I doing this? It is important to at least see that, hey, here's a group of text, and here's how we, you know, add just commas and put, you know, parentheses like a regex split, or here's how we lemonize it, or here's how we tokenize it. You know, here's how we do an n-gram. You know, these are just basic ways of splitting or dealing with text. Okay, then from there we can push it through a transformer model. Okay, there's a couple different things in a transformer model: an attention layer or self-attention layer, parallelization. Okay, but at the end of the day, really, what a transformer model does is it kind of figures out the attention or the relation of one word to other words, and it predicts the next word. And so understanding the relation of one word to another word, you can understand context. Today, I was at the restaurant and the server dropped a glass and broke it. Today, I was at the university and the server crashed and broke. Very similar words. The word server is in both sentences, but yet the context is very different. Okay, so that is one for self-attention. How does this one word relate to other words? In the past, it was not easy to do. I mean, sometimes in the past, we look at maybe one word before it. We keep it in independence. You know, they were not related to anything else. So these are some pics from the book. You can see here, write an apologetic email to Sarah for the blah, blah, blah. So the first kind of predicted token is deer, the highest probability. That over here in the slide, I don't know if you can really see my mouse, but underneath my head, I guess it's kind of hard to see. Give me 1 second, guys. Oops, no. Let's go, there we go, look at that. I can move myself around. Okay, so what happens is we feed this into a model, a neural network, you know, a bunch of neurons, pre-trained, wired, and programmed. And it says, but it does its magic, and it says, hey, if I take all 50,000 words I know, the most likely first word is deer, at let's say a 40% probability. These other words, while they may not be right or wrong, are less probable. Okay, do I have the, I do. Okay, then, so now you have one word. So now we go through the fold feed, we kind of do it over and over and over again. Okay, so we predict the first word, then we kind of go through the stack, and then we predict the second word. And we go through the process again, predict the third word. And when you really think about that, that's quite amazing. That's why a lot of these LLMs have limited context window, 4,096 context or tokens. They're getting bigger as time goes on through more advancements in the model and different math models. But at the end of the day, it's predicting all the words that it's going to say, and it's quite good at it. So we talked about self-attention, and you know, this is a little note that I highlighted. Context is vital in order to properly understand language models. Well, properly understand language. I used the example of the server today, but it could be the dog chased the squirrel because it. Now, are we talking about it meaning the squirrel or it chased a dog? And sorry about that, guys. There is no direct or perfect answer. So we can get mathematical relationships between both words. But we do know that it is either a squirrel or it is a dog. And I also have a little demo of this, but this is so hard to actually demonstrate and predict and show. But basically, that's what self-attention is. Okay, so here's kind of a little bit more about autoregressive. Write a story about the model receives initial prompt, parallelizes all the tokens, predicts probabilities for the next token. Write a short story about, then it adds an A, and then it goes through the whole process again. Write a short story about A. And you kind of see that through here. Write a short story, or whatever, you know, write a story about a cat. So it just kind of keeps going on. It keeps iterating. That's why it says first, second, third generation. Never found a good place where to put my face, just to let you all know. Okay, let's keep going. Okay, so here is a notebook. I can download this or share this if y'all want. Let me get it loaded. I moved over to my other account because some of these demos take a while to run. I don't think this one's particularly that bad, but some of them do take a while. I know a few people have had problems with the homework in terms of when they do it. and 2 or 3 people emailed me, and one of the best advices I can give you, if something doesn't work, you have some weird error, you can either delete and disconnect and delete runtime, or just change this runtime. If you change this right here, I know you don't have all these options. You have this one, maybe if you actually change this, it literally gives you a whole new machine. So it's like a whole new fresh image, whole new fresh everything. So all your variables are gone, all your data is gone. You have to re-download everything. But the thing is, you're starting all over again. You're starting from a fresh machine. And in theory, I've tested all these notebooks multiple times to make sure that they run, hopefully, fresh from the start. So just, if you have problems, like if I was to run this again, it might error out. It might give me an error down here. Like, see, it downloaded some data. I have to download that again. So, yeah, if you have a problem with notebooks, just restart it. The, the, the notebooks are shared with you, so you're not going to delete or destroy anything. You can always also download them and save them for later if you want. I have one demo today that's actually in person. Like, I have the code here because it uses a key, and I don't want to just share my key. And there's other ways to do it, but so basically, what this is going to do, this is going to show you how auto kind of regressive propagation or generation works. It generates one token at a time. We're using a Microsoft Phi 3 mini model. That doesn't really matter. Okay, and I'm trying to understand autoregressive machine learning. So that's a prompt, and we want to see how it finishes that off. So let it download, and then I'll come back. It's going to take a minute. Okay, finished downloading. You see that it's actually augmenting that. It's actually generating that. So let's add a new question. Well, now is the time for all good men. Thanks to come to the aid of the country, but I'm not 100% sure of that quote. You see how it just kind of adds on to it. Uh, even the token, like, hey, it adds a period to finish a sentence. You think it might be a space or a return. So let's try, I don't know, and I have cats and dogs. Some people like cats, but I am more of a dog person or something. So I'm just gonna hit play. So you see the autoregressive nature of this model, because I'm basically printing out one prompt at a time, or one token at a time. New token A, dog, person, period. Uh, he likes cats because they are independent. So you can kind of see it actually in action here. Hopefully you can see that. The screen here. Yeah, you can see that. And that's really neat, like I said. So that kind of gives you the idea of how prediction works. Okay. And that's, has to do with temperature and other things like that. So if you guys want that code, I can give it to you. No big deal. It works without any APIs or anything else like that. You can run it on probably just the T4. It should run without problems. So, okay, let's get back to the lecture. Uh, Actually, there's another notebook. Attention is all you need. So this notebook, this code demo, I think this one might take a little bit. But in a nutshell, again, it's really hard to try to understand the difference between. Maybe this one doesn't run all. Basically, what we're going to do now is take a sentence and try to compare the non attention mechanism, okay, where every word is counted individually. Okay, each output token is only depends on its corresponding input token. Okay, so the input only basically, the output only is relied on the input token. You know, basically there's independence. There's no context. Okay, and the problem with that is, and again, this is the way it used to be done, I guess, pre-2006, pre-2007. You know, there's no context there. But when we start having that context, okay, where each token is influenced by all the other tokens, okay. You know, I think the cat sat on the mat, okay. We have that, we start seeing relationships between cat and sat, on, you know, mat. So you see here, and I have a nice little visual that kind of shows relationships, okay. So non-attention, independent token processing, how words are related. And it's kind of just scattered. I guess I should update this with the words or something else like that. That might help. You know, BERT first token, attention. And I put some more terms down here. You know, it classifies it, things like that. But the relationship, even in a short sentence like that, the cat's out on the mat, is vital. You know, so the non-attention, each row is processed independently, or each token is processed independently. Sorry, I'm thinking about sentence transformers. No information is shared between tokens. So we don't know, you know, the cat is given the same importance as the and on. Attention shows how much each token pays attention to others. Values sum from basically 0 to 1 for each row. Average interaction is 0.25. So yeah. Like I said, it is hard to actually understand the significance of it. And I don't know how important it is per se, but now we've kind of learned two important things. We've seen the autoregressive model, the autoregressive nature of predicting the next token in autoregressive tokens in terms of like GPTs. Because, you know, BERT does a little, it does like masking, and it does slightly different. But we also show how attention is so important. Okay. Now, I'm not going to go into a ton of detail on these, but sparse, I think I have sparse local attention. Yeah, that's the only one that I really kind of care about a lot. But basically, when we deal with transformers and self-attention, we have to kind of keep track of the whole paragraph of everything. And that can be computationally, or at least memory-wise, expensive, okay? So your book talks about sparse versus local attention, okay? And the idea is that you can kind of say, hey, this is more important locally versus it's less important, okay? And if we think about this, you know, one of the analogies I always like to use on sparse versus local attention is if we look at stock prices, you know, and I always go back to that Henry Ford. I don't know how many CEOs Ford Motor Company has. I probably should look it up. But the first 2 or 3 CEOs don't have as big of impact on the stock prices as the current CEO. The local attention is on the local or the current CEOs. Now, that's not to say that the sparse CEOs, the past CEOs, didn't have any attention or didn't have any influence, but it's just not as great. And that's always one of the best ways I can think to kind of explain it. You know, and you can kind of see that. I'll come back to the slide right here. We look at, you know, things more recently. I mean, if, you know, just imagine these are decades. 1920, 1910, 1920, 1930, 1940, 1950, okay? Well, if we want to kind of predict stock prices, maybe we only want to look at the CEOs from 1940, 1950, 1960s, and 1970s, okay? And having that local attention can allow us to increase the token size. It can allow us to interact with the model and predict and understand much better. Your book talked about flash attention And Flash Attention came out a couple of years ago. It's still hard to ever be. I have attention, and it's great. Basically, it just kind of reduces computational bandwidth or memory bandwidth. So if you don't know, when you do machine learning, you try to load as much of the model, as much of the brain onto the GPU. Anything that doesn't get loaded onto the GPU might have to float or share with a system memory, the computer memory. Now, why is that good or bad? Well, in theory, computer memory is much more expansive, a lot larger, but also a lot slower. A lot slower. You know, we think about a highway. A highway only goes to very few spots, which is very fast. Where dirt roads can almost go anywhere in the country, but generally the speed limit on dirt roads is 25 miles per hour. Now, with GPUs, you know, like NVIDIA, ROC, AMD cards, the performance difference is night and day. And so Flash Attention kind of deals with some of these things. Now, another issue is multi-query attention or group query attention. And I think, pretty sure your book, I don't have a picture of it. It basically has to do with what are we kind of focusing on, or are we, you know, or can we summarize the attention? You know, if I look at all the different, if I'm looking for stock performance, let's say, well, my queried or my grouped attention, my multi-attention might only be the CEOs of all those companies currently. So I can kind of summarize that into one attention. You know, I don't need all the CEOs of all the Fortune 500 of all times right now. Maybe I just need the current CEOs, and so I can summarize it, or I can summarize the tokens. I guess that'd be a good way to kind of explain it. Let's keep going. So on this one, again, the first slide, and see, it's something called a long document transformer or a long transformer or a long tail, or not a long document model. Has some terms, but that's one way to think about it. And why is that important? You're like, oh, 4,000 words. It is really not that much. You know, ChatGPT 3.5 and the original DeepSeek LLM, they had 4,000 token inputs, and it's just, trust me when I say it's not that much. GPT-4 and GPT-4 like Turbo 32K, things like that, have much larger tokens. Llama from Meta, 3.3. I think 3.1 both have 128K token. I think Claude has 128K token. Input K is thousands, just to let you know. The new Google models are floating between 1 and 2 million tokens, so much larger. Now, this is down here on the bottom here. Let me actually move my head, just oops, real quick so you can actually see the whole thing. Okay, so I guess this way, oops, other way, that way. Oh, that way, there we go. That is some of my token use for Open Router. And so like, it's kind of hard to see, but in one day I use just under 14 million tokens. And I mean, if you think about that, at 4,000 tokens, you use 14 million tokens. I'm not doing anything crazy. This is just my own personal account. This is not my work account. I'm sure my work account is 10 times larger than this. This is just my own kind of research, my own poking around, just own playing account. I'm using 14 million tokens in one day. You know, some of these other days, 7 million. And so what that means at the end of the day is that, you know, if I have to read a book, if I have to read Harry Potter, you know, or War and Peace, a very big book, but you only give me 4 pages at a time, it becomes really annoying. You know, you give me 4 pages, I read 2 or 3, then you know, I have to wait a day, and then read the next 4, and then wait a day, and read the, it was very annoying. Where if you just hand me the complete Harry Potter or War and Peace or encyclopedia or whatever, if you can hand me the complete corpus, and I can absorb it, I can summarize it, I can look for themes, I can play with it, I can enjoy the book, I can take my time, I can read it fast, I can do whatever I want to do. because I have access to all the information, and I can get more done. So that's why token size matters. There wasn't much. Again, like I said, I did leave my video up, or I will leave my video from last year. NLP is particularly good at summarization. Now, I don't know if the rule book goes into a whole lot of it. I think I've done a demo in Notebook LM, but basically you can put this book, if you have a PDF of it, up there and say, hey, summarize this chapter. You can put research papers up there and say, hey, summarize this. Because GPTs and BERTs and things like that, like NLPs and natural language processing machine learning models, are very, very, very good at most of the time summarizing information. Again, it comes back to tokens. As long as it fits within all the token window, the token input, it will summarize it very, very well. Now, why do we want to summarize? I was trying to think, because again, this is a different book. Well, we get a lot more information than we did in the past. If we compare the amount of information we see in 2025 compared to the amount of information we see in 2015, compared to the amount of information we see in 2005, and we just go back, the amount of information availability to us is maybe not exponentially increasing, but it is increasing at a vast rate. And we can't absorb it all, but yet we're expected somehow to know it all, or at least understand it all, or research it. Do you think Google keeps getting smaller each year? If I look for LDA, which I think is the topic we're talking about, or dimension reduction, do you think this year there's going to be more on that topic than last year? Yes, each year there's more and more stuff. So I have to find, as a knowledge worker, I have to find ways to distill that information. Okay, so that's information overload. There's just more information, time and efficiency. Now that, let's say there's 10 websites on sentence transformers. Last year, maybe there was one. I have to figure out what one I want to read. I need to be able to focus my productivity. Additionally, the original idea of attention is all you need was to translate from one language to another language. Well, now the idea, just as, at least in my mind, different languages, different countries, different borders has almost been obliterated. Now they're still physically there, but my cell phone is a 916 area code. Many of you have a 702 area code. My wife has a 415 area code. Many years ago, to call different area codes, you used to have to pay more. You have to charge more. It was a hassle. You just have to have a long distance carrier and all this stuff. Now that's all gone. That's been all obliterated. I think, maybe not right now, but in the next year or two, a lot of different languages and a lot of those maybe access problems will be gone. I have a document that I'm using for a research project, and I think it's in Japanese. I can just translate it in real time. Today, I was on a French site. Boom, I click right mouse click on Google, translate into English. Boom, it's done. In real time, it translates right into English. Okay? So, amazing. Support for multiple languages, customization, personalization. Maybe I want something to be written at a dumber level, which I know sounds horrible, but it's very, very important because there's some really complex subjects that are just insanely hard. And if I can take it and ingest it at a easier level, then ingest it again maybe at a collegiate level, and then ingest it again at a graduate level, then then I'll slowly start learning it. Why do we give people learner's permits when they learn to drive here in this country? So that they can grow and personalize things, Okay. So these are the older methods, kind of before ChatGPT, before transformers. Okay. And so TDM, text term document matrix, it can be basically contains a frequency, the count of words that appear in a document. Now, that could be really good because the, and, or might appear a lot. You can maybe get rid of those. but maybe you're looking for some legalese term. Maybe you're looking for decomposition, the word right below it. So, once we have that matrix, we can kind of figure out how often that word appears. And does it appear a lot in one sentence? Does it appear a lot on one page? Does it appear a lot in the document? And how does that term compare, or how does that term compare in that document to other documents? If I take a neuroscience handbook compared to a math handbook, I bet the word dopamine appears much more frequently in my neuroscience handbook than in my math book. Not to say that let's say, I know, serotonin, we'll go serotonin. Not to say that serotonin doesn't appear in both books, but the frequency of it is very, very different. And we'll see that, but dimensional reduction. So there's a couple different types of dimensional reduction. And basically all that is doing is we're just trying to find a way to compress or to get something that we can understand better. There might be extra noise in there that we don't need, and we can kind of maybe, and noise is not really the best word to use, but if we can kind of filter on what's important, okay? So if somebody calls me and I say, hey, I'm going, let's say, westbound down Flamingo, which is state route, let's say 123, at 23.89 miles per hour. It's 77 degrees out, and I'm driving a white vehicle, and I've hit 3 red lights and 2 green lights. There's a lot of information there we might not need if somebody just said, how far away are you? Or how fast are you going? If you want to know how fast I'm going, 35 miles per hour. 70 kilometers an hour, or kilometers an hour, whatever. So we have to figure out what is valuable and what's not valuable. There's different ways to do that. UMAP, PCA, there's different ways. And I'm sure other classes have talked about that. But for this class, that's all dimensional reduction is. There's a couple of different types of summarization. The other book went into, this book doesn't go into it, but at the end of the day, move my face again. Nope. I'll go right here in the middle. No, I like it up here. Okay, so there we go. So extractive summarizations are abstract, okay? So one, if you look at Notebook LM, Notebook LM takes what I upload and just kind of uses that as a source of truth, okay? And the goal is to basically pull out or understand what I'm looking at and pull out the most important points, okay? So if I'm looking at a legal document, that's what I would like to use. I don't want to make up new things. I need to be able to identify the forensic evidence, the case law in that document. If I go over here to the other side to abstractive, so hard to say, of summarization, where we still need to understand the main concept, but then we can paraphrase it, we can change it, we can add on to it. Okay. It's a very nice day except for the rain. If I, if I need to maybe change that a little bit, it's a wonderful day outside except for the rain, or it's raining, but other than that, it's a very nice day. So, we understand the main concept, but we kind of rephrase it in a more, I don't want to say creative manner, but we rephrase it in a way that basically matches the context or the intent of the original sentence or the original idea. It could be more than one sentence. Mm-hmm. Okay, yeah, exactly. So this is more like Notebook LM. If you guys play with Notebook LM, it's important to retain the original phrasing, such as legal documents, medical records. We don't want to rewrite it. We just want to disseminate, reduce, focus, things like that. Yes, there we go. The main drawback is that summary may lack the fluency or coherence of a single sentences that are taken out of the original context. Whereas the next type, oops, there we go. is generative based. You know, we can all tell that on the video, that's just a piece of paper. But the piece of paper has a stencil cut out, and so we can understand that. We can abstract, we can understand what it's saying. This is what the newer models do, the transformer models. Now, again, like I said, it's more complex due to the ability to, or the need to implement transformers, self-attention, and other things. But also, again, now we can summarize things with a lot greater detail. We can convert from one language to another language. There's a lot more we can do. I have a sentiment analysis demo, I believe. I think that's next week. But basically what that is we want to know how either person, customer, thing feels about something else. Now, a lot of these are semi-subjective, subjective. You use a bad model, and it might not be able to pull the sentiment or the intent as well as other models. But if I was to grab all the news articles or all the news broadcasts for any particular day, and then look to, hey, are you talking positively about the stock market going down or negatively about the stock market going down? What information can I derive from that? There's a lot of research that correlates news sentiment of a stock to its price. Shows you how important it is. But there's a lot of reasons that we and other people look at sentiment analysis. You know, I use voice of the customer, brand monitoring, see if people are saying negative things about social media monitoring, analyzing customer reviews. I mean, are people being sarcastic, or are they just saying, oh, yeah, great product for a $5 gift card, or do they really mean what they say? But like I said, down towards the bottom, subjective text, it's hard to really pull out or understand mood, intention, or feeling. That's why I try to have my face on these videos, because I can say something like, oh, not another slide, or oh, not another slide, and it changes the inflection and tonality of what I say. Types of sentiment analysis, you know, polarity detection, emotion detection. You can skip all this. Challenges, yeah, sarcasm and irony, as I was mentioning. Contextual meaning. So if you have a paragraph where you basically talk negatively about something, and then you have another paragraph where you kind of like act like you care or you're being sarcastic, it might be hard for the machine to link the two together. So that's what the contextual meaning is. Also, you know, tide roll, for example, might have different meanings here versus down south, and you know, I don't know, Georgia, Mississippi, places like that. Words have regional variations. You know, that's kind of the last two slides, making it harder. You know, I believe, I could be wrong, but in the South they use the word love and honey a lot more, I guess, openly than they do here. Dude maybe is used in California where it's not used in the South. So these differences can make it hard for a sentiment analysis machine learning model to really understand the differences. But the big picture, hey, that was a great movie. Oh my God, food was so good. Traffic was so bad today. You know, things like that, the machine should be able to pick up. Nope, need that. It just talks a little bit about it. Okay, so big picture idea, remember, there's really two types of, I would say, learning or data or whatever. Supervised and unsupervised. Supervised and unsupervised. At the end of the day, clustering and you know, BERT and a lot of these other things are unsupervised learning methods. We don't have a label. We don't know if that sentence is positive or negative. When I say, not another hot day, we don't know if I'm being happy or negative. You know, if it's 120 degrees outside in the summertime in Vegas, I might be negative. If I say, oh, not another hot day, I don't know, maybe that could be very positive. So somehow we could have labeled data saying, hey, this is a good sentence or this is a bad sentence. Then we can do supervised learning. We can take our learning to the next level. We can use better machine learning models. The problem is who's going to put those labels on? It's human labor and it's humanly intensive. You know, if I have 200 images and, you know, I need to label them as good or bad images, you know, maybe, I don't know, maybe they're out of focus or maybe they're, you know, the subject is like skewed or maybe they're not very good product shots for, you know, like think of a business and think of a stock. You know, maybe I have 200 pictures of my root beer can. Well, I need to, you know, have somebody sit down and look at all 200 images and write good image, blurry, background too busy. And that takes time. That's what supervised learning is. It has a label that we're training against. Unsupervised does not. So there we go. I will post both of the links to the two code demos, Autoregressive and the attention versus non-attention tokens. You don't really need to run them. There's nothing related to that, but if you want to, feel free. Don't forget to work on the research project. It's due Friday. Don't stress about the midterm. Don't stress about the final. I think the class average so far is like 110, so everyone's doing really well. But remember, if you're late on the research project, it drops really quickly. So please don't be late. Other than that, have a great day.